According to the cloud. All right. Wonderful. Okay. All right. And so tonight, I'm very excited. I hope some of you all are too, because I don't know if you heard about the Vera Rubin Telescope, but it's pretty exciting, and we're going to see why here. Thank you so much for Professor Greenstreet to come down here. Commuted from Bothell in rush hour traffic, so thank you. Let me just introduce Sarah real quick. Sarah is a research scientist with the DiRAC. Am I saying pronounce it right? DiRAC? DiRAC. Okay, yeah. So Sarah's a research scientist with the DiRAC Institute. She studies small bodies throughout the solar system, ranging from the near-Earth objects and main belt asteroids in the inner solar system to Jupiter, Trojans, and Kuiper belt objects near and beyond giant planets. Her research program focuses on orbital dynamics of solar systems, small bodies, including resonant dynamics, really cool, near-Earth asteroids, and on retrograde, backwards around the sun, orbits. Temporary planetary co-orbitals, impact and crater formation rates, in particular on Pluto and Charon, asteroid Earth impact probabilities and hazard mitigation, and asteroid observations. That was a lot of cool stuff. Like every single one of those I wanted to learn more about. She is also focused on creating open source software and increasing the accessibility of software packages commonly used across the field of small body science. For more information, please visit, this is convenient, sarahgreenstreet.com. I'm glad you got that. I was like, I might have, yeah. And so tonight's program on the Rubin Vera Telescope and DiRAC, I'd like to introduce you, Affiliate Assistant Professor of the University of Washington, Professor Sarah Greenstreet, if we could have a round of applause here. Yeah. All right, as we get set up. Oh, and I'll put the lights in a second.
Away. And I think the way behind the bar at the top of the screen.
That one's kind of
an easy way to hide floating meeting controls. Okay. I think that did it. Okay. All right. Did we want to dim the
I just realized I forgot to share my screen for the intros on the Zoom, but y'all have seen that slide. Yeah. Everybody comfortable?
It's gonna get nice and dark. Okay. All right. I'm gonna get my timer started so that I make sure I try to stay on time and don't ramble on for too long. Yes, can everybody online hear me? Okay, I suppose we should probably check that we're getting a thumbs up from people online as well.
Let's see, anybody on Zoom? Oh yeah, Alan says you sound great.
Yes, okay.
So we're good on the Zoom room.
Okay, all right. Well, hello everyone. Thank you so much for the invitation to get to come speak with all of you today. And thank you as well for all of the outreach work that you guys do in the local community. I think getting to get people excited about astronomy and especially making it accessible to people is really important. And so thank you for all of the work that you do for our local community in that regard. Before I start talking about the Rubin Observatory and its connection to the DiRAC Institute here at the University of Washington, I thought I would give a little bit more background information about myself, if I can figure out how to advance my slide. Do you need me to talk louder? I can try to talk louder.
See, I think testing.
Oh, okay.
Welcome. All right. Sorry, that's the other way. All right. Let's see.
We can move this over here a little bit more. Okay, I will stand on this side. Is that a little bit better for everybody? Okay. Let's see. I still need to figure out how to share my slides or how to advance my slides.
Space bars.
Yeah. Tried the space bar. And the buttons. Okay, I guess I'm going to click. Okay, I can do that. All right. All right. So a little bit more about me and my background. I am a planetary scientist or a solar system scientist. As Erin said, my research largely focuses on studying small bodies, asteroids mostly across the solar system. I study everything from things that live very close to the sun all the way to things that live out beyond the orbit of Pluto and many of the different objects in between. I study how asteroids can impact large bodies and make craters on their surfaces, and I study how asteroids can have their orbits change over long periods of time as they interact gravitationally with the planet. I received my PhD from the University of British Columbia in 2015. Although I'm not Canadian, it's usually the follow-up question I get to that. And after graduating, I did a postdoctoral fellowship at Las Cumbres Observatory, which has its headquarters in Santa Barbara. But they have built and operate something like at least 25 or more telescopes all over the world. And so it was a really fascinating place to get to work at for a few years. And then after that, I came here to become a member of the Data Intensive Research in Astrophysics and Cosmology, or DiRAC Institute, here in the Astronomy Department at UW. I started as a postdoctoral fellow here, before then becoming a research scientist, and now recently transitioning to an affiliate assistant professor here. So I've been a part of the DiRAC Institute for about the past 6 years. I also very recently started as an assistant astronomer at the National Science Foundation's NOIR Lab, which stands for National Optical Infrared Astronomy Research Laboratory, which is a mouthful. But at NOIR Lab, I now work for Rubin Observatory as a member of the community science team, which I'll talk a little bit about later. And I've also been involved with the science community's efforts to get ready for Rubin Observatory through a leadership position within the International Rubin Observatory Solar System Science Collaboration as well, which I'll also talk about briefly at the end. So before I actually start talking again about Rubin and the DiRAC Institute, I wanted to give a little bit more background and context as to how we have advanced through astronomy over time that has led us to this point shortly before Rubin Observatory is going to start doing amazing things. So as I think many of us are would say, if we want to say what an astronomer is, largely it's somebody who uses telescopes to study objects and phenomena in the night sky, and then share what they learn with other people, which I think many of us in this room have a very strong passion for. And traditionally, this is how astronomy has been done for a very long time. Even at the professional level, for hundreds of years, we find a specific object that we think is really interesting, that we want to go learn more about. We then try to get time on large telescopes to then be able to go take images, perhaps spectra of these objects. We then take those images and we analyze them in order to try to understand the object that we were interested in as best we can, and then we publish a paper on that specific object. And this is really how astronomy has been done for a very long time, until the past couple of decades when technology has really taken off and started to change much of our daily lives as well as the field of astronomy. And so with the development of CCDs and of course the internet, and the ability to run large-scale simulations on computing clusters, which is a large part of what my own research entails, all of this has really led us into a new era of astronomy. One of the best examples of this is the Sloan Digital Sky Survey, which many of you may be familiar with. SDSS was started by a consortium with the University of Washington and Princeton University. And it really changed how we use telescopes, because rather than being used to point at specific objects on the sky in order to take observations of a given object as requested by individual astronomers throughout the night, the Sloan Digital Sky Survey is really designed to be able to take a survey of the night sky taking as many images covering the night sky as possible to produce as much data and information as possible for us to then be able to go mine and look at. And so to get an idea of how this is different than what we usually do in astronomy, for example, we can look at this rather famous image of the active star forming region in the Eagle Nebula that was taken by the Hubble Space Telescope. If we compare this image, where Hubble is very good at taking images, as has traditionally been done in astronomy, of a specific object in a very small patch of the sky. If we compare this to something we're very used to seeing in the night sky, which is the full moon, this Hubble image, like most Hubble images, are actually a very small point on the sky focused on a very specific object, like the Eagle Nebula in this case. If we then compare this to what the Sloan Digital Sky Survey looks at, when it takes an image on the sky, its image is roughly 10 times the area, the surface area of the moon in a single image. And Sloan then takes an image, several images of the night sky, kind of tiling the night sky, trying to cover as much of the sky as possible. And so if we map out where all of these images are projected on the night sky, we can see that the Sloan Digital Sky Survey over its first 10 years of operation really took images of as much of the visible sky as it could see. It made something like 1.2 billion observations of stars and galaxies, producing about 20 terabytes of raw imaging data within its first 10 years of operation. It's still in operation today, 25 years later. And this amount of data was really the first time that we needed to start thinking about how to store all of this data in large databases and then be able to process that data in a much more automated way, because these images are constantly being taken on the telescope every single night for decades at a time. So being able to take all of those images, process them in an automated way in order to extract all of the information about the light sources in those images and be able to put it into an online database that would be available for the science community to then go be able to pull out what information they need to be able to do their science. Is a much different way of doing astronomy than we have done for a long time. And so if we look at the amount of data that was produced in just the first 10 years of SDSS alone, we would get something like this giant data table that has more than 1.2 billion rows, where every row is a different observation, and there's roughly 500 columns, where each of those columns is a different piece of information about each of those more than 1.2 billion observations, which is kind of a mind-boggling amount of data that we now have available to be able to do our science. So in order to be able to make this a bit more manageable, there were also tools that were put together with the Sloan database that allows somebody to ask a question and pull a subset of that data out to be able to do something like get all of the positions and magnitudes for the stars within 1 square degree of a given galactic latitude and longitude, which could then give us something that's more manageable with a table that has roughly 70,000 rows, which is of course still a lot of data, but perhaps more manageable because now we've also reduced the amount of information, so the number of columns that we have in that data as well. And this, the best way to be able to understand this data is to visualize it. And so we can make something we commonly do in astronomy when looking at stars. We can make a color magnitude diagram, which can then tell us more about how the stars within the Milky Way are distributed, what type of stars are located in that part of the Milky Way. We've got 70,000 stars in this one plot alone from 1 square degree patch of sky. We could then do the same thing for a different patch of sky, get another group of data that's another some tens of thousands of rows, make another plot like this, and we can compare the two and look for any differences between them that might tell us how the stars in different parts of the Milky Way might differ from each other. And because there are so many objects in every single one of these small patches of sky that we can look at, this really then allowed us to start getting a very detailed map of the structure of the stars in the Milky Way that we never were able to do before this kind of a data set was available. And so this is really the power of these very large data sets. 10 years ago, being able to do this kind of a project would have been much different. You would have had to write a very competitive proposal to try to observe at some of the top telescopes in the world. If you were granted time, you would then have to do a multi-night observing campaign in order to collect all of your data to then be able to analyze it and do your science. So really the challenge was trying to get the data in order to be able to do your science. But now with these large surveys like SDSS, that data is already sitting there waiting to be used. And really now the challenge is being able to know the right questions to ask and how to use the tools that are available to be able to access the data to answer those questions that can then tell us things on a much grander scale about the universe than we've ever been able to do before. And so this is really what the Sloan Digital Sky Survey did for astronomy by allowing us to have more evidence than ever for the existence of dark matter and dark energy in the universe, having a more detailed map of the Milky Way than we ever had before, finding more than ever of the most uncommon and rare objects across the sky, and even get a more detailed understanding of the asteroids in our solar system as well. And so this really drove astronomy to a new era where we're really now driven by these very large data sets and needing to know how to be able to do our astronomy using these data sets. And so as astronomers, we now not so much do we go to telescopes to collect more data about small numbers of objects. We already have a huge amount of data that's available to us. And really what we now do is try to figure out how to extract that information out of these databases by writing algorithms and code and tools that can pull that information out so that we can then make these very grand, large-scale inferences about the universe. And so our day-to-day work is really more like someone who works at Microsoft or Google than compared to how astronomers used to operate on a daily basis, even 20 years ago. And so this has brought a dramatic shift to what astronomy actually is, what astronomers do today, and what is actually needed to be able to be successful as an astronomer. And so this is the reason that the University of Washington launched the Data Intensive Research in Astrophysics and Cosmology, or DiRAC Institute, 6 years ago, back in 2017, where our mission within DiRAC is really to be able to hire talented, driven individuals who have a diverse technical background and knowledge base in order to help them foster big ideas, in order to think outside of the box with building algorithms and tools that can extract information out of these huge data sets that we have in order to make incredible discoveries. And then the students and the postdocs that come through our program can then go out into the field ready to be leaders and to thrive in this new era of data-driven astronomy. And so this is really what we have been doing within the DiRAC Institute for the past 6 years. And a lot of that work has continued to be to utilize current surveys and also look toward the future. So an example of this, another current survey, it's called the Zwicky Transient Facility, which is being run on the Palomar Observatory in California. ZTF, as we often call it, has been producing something like 300 million source detections every single night. And with that much data that's coming in every single night, what we really want to know is, did anything change over time? Is anything doing anything interesting, any of these light sources? And so one of our former research scientists, Maria Patterson, wrote an algorithm that can actually look at the data that's coming in on a nightly basis to look and see if anything different happened and be able to alert the community. So for example, if we see a tidal disruption event where a star is getting pulled apart by a black hole or a new supernova suddenly explodes, Maria's algorithm will be able to detect that, and then it sends out an alert to the entire science community that this event happened, which then allows the community to be able to go get more observations of that object and learn more information so that they can do their exciting science. So this has really enabled half a decade of discovery with CTF that wouldn't have been possible without Maria's alert system. Another example of this, one of our postdoctoral fellows in DiRAC, who joined us a couple years ago, he developed a new algorithm with his thesis advisor, Gary Bernstein, that used a data set that had already been available for a number of years to dig through that data in order to find anything interesting. And they discovered the largest comet that has now ever been found. It's an Oort cloud comet that had just been sitting in the data for the past 7 years, waiting for somebody to write the right piece of code that could extract it out of the data and make that amazing discovery. Similarly, research scientist Ari Hines has developed another piece of code that recently discovered a potentially hazardous object that had been missed by all of the other observatories that have been looking for these objects. And again, this object had been sitting in the data for a number of years, and it just needed the right piece of code that could pull this out of the data. And of course, finding these type of potentially hazardous asteroids is really helpful for us to know about. And so we've been enabling these amazing discoveries by developing these new type of algorithms that can utilize these vast data sets that we have. You may also have seen some of these pesky little light sources that like to go across the night sky. We find these very annoying in many of our images because when we want to look at deep things, we take long exposures, and these satellite constellations leave these terrible, horrible streaks across our images that make it very hard to do science with these images. And so one of our research scientists, Meredith Rawls, and graduate student Dino Bektezovic have been trying to raise awareness about the threat to astronomy from these satellite swarms, and have been also trying to develop algorithms that can take these images that have these satellite streaks in them and be able to remove those streaks so that these images are now actually more amenable to us doing astronomy with them, which is a great help. So the list can go on and on with the number of ways in which the researchers and the students that have come through the DiRAC Institute have been able to develop these algorithms in order to make these incredible discoveries. In the past 6 years, our researchers have co-authored something like 400 papers that have more than 13,000 citations. And so we've really been making huge strides in the field of astronomy with the way that we are now starting to tackle astronomy. And we've had a number of students and postdocs that have come through. And of course, we've been writing these pieces of code in order to use the current data sets that we already have available, but we've also always been looking toward the future because we know there is another data set that is coming that is going to dwarf everything we have ever known before. And that is with the Vera C Rubin Observatory. The Rubin Observatory also has very deep ties to the University of Washington. It was co-founded in part by the University of Washington, and it was kickstarted by gifts from Charles Simonyi and Bill Gates, who really gave the project enough funding for NSF to then be able to take it over as its now flagship project. Also, our own Professor Jelko Ivazic is the current director of the Rubin Observatory. And so we have a number of deep ties here at the University of Washington to the Rubin Observatory. Rubin is being built. It's currently still under construction. It's being built atop Cerro Pachon in Chile. It's this massive building in the bottom of the screen here. Kind of off on the middle right side is the Rubin Auxiliary Telescope. And then you can see up along the ridge, if you follow the ridge line, first you come to Gemini South Telescope, and then in the far distance you can see the SOAR telescope as well. So there's a number of big telescopes on this mountaintop, but Rubin is now the biggest. This is a picture of what the observatory looked like in March of this year. It's getting very close to completion. And this was a really important milestone for us because in March, of this year was when the telescope mount assembly was deemed substantially complete. Rubin is going to have an 8.4 meter primary mirror, so it's a massive telescope, and it impressively can boast being the fastest optical telescope in the world. So I'm going to start this little movie, which is from December of last year, of the telescope mount assembly moving. This is a 200-ton piece of steel that can slew 180 degrees in about 20 to 30 seconds, which is incredibly impressive. It looks like this should be a sped up video. This is actually in real time, which it's an incredible feat for this massive piece of equipment. There's a regenerative braking system under the footplate here that operates much like how electric vehicles are charged these days, where as the telescope brakes, it charges up the batteries, which is one of the ways that helps it be able to move so quickly. Another reason that it can move quickly, you'll notice it's got a pretty compact design. Rubin has 3 mirrors, but it's unique in that the primary and tertiary mirrors are actually carved out of a single piece of glass, which is part of what gives it this very compact design and allows it in part to move so quickly. To get an idea of how big 8.4 meters is, this is the primary and tertiary mirror cast with a bunch of the Rubin crew also here for scale. And you can almost kind of make out how in the middle here, there's a different radius in the center where the tertiary mirror sits than the primary is out on the out-hand side. This is a schematic view of the Rubin Observatory, the entire observatory. If you look on the lower right here, the observatory has its own machine shop, because if this 8.5 meter telescope breaks, it's sitting on the top of a mountain in Chile. There's not really somewhere we can take it to get it repaired. So there's a machine shop on site to be able to make any repairs that might be needed to the telescope. You can also see the maintenance floor here, which I actually have a picture of, that has a number of important pieces of equipment in here as well. Kind of in the back middle is the mirror coating chamber, so that every few years, as the mirror actually needs to be recoated in order to maintain its high performance, it can be moved down to the maintenance floor here and be recoated. You can see in the middle, this is the primary and tertiary mirror that's actually sitting there. And then the big blue and black thing is a mock version of the LSST camera. The actual camera hasn't been delivered to the site yet. It's the last piece of major equipment that we're waiting to get delivered to the site. Also, in order to get the mirror from the maintenance floor up into the dome, in the middle here, you can see a 27-meter vertical lift that will be able to move the telescope from down below up to above. So I've got another movie here of a drone flying around the dome. You can see how massive this is. On the left, there's a crane here with a couple people at the top actually working on the telescope. And you can see the doors on the dome here that will open when it's time to observe. And on the back side here, on the left, you can see the rails for the doors that can open on the back side of the dome in order for the mirror to go in and out of the dome. And pretty soon here is going to come to a different view. I think it's incredible looking at these videos. You can really tell that this really is on a mountaintop with these sheer cliffs and clear drop-offs, just not very far from where the observatory actually sits. There's more people on the left here. There's some people at the top of this little crane here doing some work, and there's a couple people up on the catwalk here. But here you can see this is the roof of that 27-meter lift as it can come up. It's got a roof to cover the mirror, as the mirror can then go in and out of the dome, where the dome itself is about 30 meters by 30 meters. Here's another picture of the observatory with the doors open on the dome, and you can see the telescope mount assembly inside as well. So Rubin is going to be repeatedly imaging the visible sky down to about 24th magnitude over a 10-year period. On a nightly basis, it's expected to produce about 20 terabytes of raw data. And if you remember, when I was talking about the Sloan Digital Sky Survey, this is how much raw data SDSS produced in 10 years of operation. Rubin is going to do 10 years of the SDSS every single night for 10 years. This is going to produce a data set like nothing we've ever had before. Over the 10-year period, it's going to produce something like 60 petabytes of raw data, which is a lot of data to store and need to be able to sift through in order to make discoveries. This data is going to include 30 trillion observations of 40 billion stars, galaxies, and asteroids. And so we in the astronomy community have really been salivating, waiting for this telescope to come online because of the incredible amount of data that's really hard to fathom that we're very soon going to have available to us. In part, all of those observations are going to be possible by the LSST camera, which is the largest camera, astronomical camera ever made. It's about the size of a small car. The primary lens is about 5.5 feet in diameter. I believe it's also the largest optical lens in the world. Sorry, I think this is in the way. I'm going to move this down here so that you can see better here. Okay. Where am I? Okay. And this is an exploded view of the LSST camera as well. So you can see the primary lens on the left, and then there's the secondary and tertiary lenses. I think the tertiary lens is still something like 3 feet in diameter, so it's still very large. Then there's the shutter and the filter exchange mechanism. The camera is going to have a 6-filter system in the typical UGRIZY filters. And then it has a very impressive 3.2 gigapixel CCD mosaic, which will be cooled by a cryostat to minus 100 degrees Celsius. Here's another view of the telescope in its more compact, realistic form. The camera itself weighs something like 3 tons, which is very impressive. It's going to have about a 10 square degree field of view, and it will have a readout of about 1.6 billion pixels per second, which is also very exciting and impressive.
Sorry, did you repeat?
Those are the different filter bands, the different wavelengths. Yeah. This is a picture of the mock LSST camera being tested and getting hooked up to the back of the telescope mount assembly by some of the Rubin engineers. And this is a picture, kind of an edge-on picture of the LSST camera focal plane. Here you can see another view of the focal plane. This has some of the CCD rafts that are pulled down as some of the workers are working on the camera. You can also see how massive this camera is by the scale of the people that are also working on the camera here. And I think this is an absolutely beautiful picture of the camera looking down the nose of the camera to the focal plane in the back here. It's an optical telescope, but the wavelengths kind of start to leak into the infrared range a little bit. And this is the first image that was taken with the LSST camera focal plane. This is Vera Rubin. And for those of you who don't know who Vera Rubin was, she worked as an astronomer at the Carnegie Institute in Washington, D.C. in the 1950s. And in a nutshell, she was the one that gave us the first observational evidence for the existence of dark matter. She was studying how stars rotate, how fast they rotate around the centers of other galaxies. And rather than finding that as the stars move farther away from the center of the galaxy, that they move more slowly, she actually found that they were moving about the same speed, no matter how far away from the center of the galaxy the stars were. In fact, the things on the edges, the stars on the edges were moving so quickly that if they were only held in place to the galaxy by the visible matter in that galaxy, they should have escaped from the galaxy and no longer been part of the galaxy. And so this was the first evidence that there's something else that's present that we can't see that's keeping these stars as they're moving so quickly around the center of the galaxy to keep them in place as part of the galaxy. So discovering the observational evidence for dark matter was only one of the many contributions that Vera Rubin made to astronomy. And for a little bit of history, the Rubin Observatory was originally named the Large Synoptic Survey Telescope, or LSST, and then in 2019, it was renamed the Vera C Rubin Observatory. And so, to have a little bit of helpful terminology, there's a lot of acronyms in astronomy always, we say that the Vera C Rubin Observatory is going to perform the legacy survey of space and time. So we kept that LSST acronym, which is helpful. And it will perform the survey using the Simony Survey Telescope, which is named after Charles Simony, who made the initial gift that had made the entire observatory possible. There are 4 key science themes that are the science pillars for LSST and the Rubin Observatory. These are better understanding dark matter and dark energy, mapping the Milky Way, getting a better inventory of the objects in the solar system, and exploring the transient optical sky. So I'm going to talk about one of these, which is solar system science, because this is my area of astronomy. And I'm going to talk about some of the areas of solar system astronomy that we're going to be able to make some very exciting discoveries with the Rubin Observatory. So our understanding of the solar system is about to vastly change. Today, we know of about 1 million objects in our solar system, which have taken us the past 200 years of discovery in order to find. And with the Rubin Observatory, we're going to discover another 1 million objects in the first 3 to 6 months of the survey running. And we're going to find a total of 5 million new solar system objects by the time the 10-year survey has completed. That is a mind-boggling, exciting amount of new discoveries that we're going to have in the solar system alone that really makes this an unprecedented data set that is going to allow unfathomable discoveries. One of the groups of bodies in the solar system that Rubin is going to make a big difference for are the near-Earth objects. We currently know about 20,000 near-Earth objects today, and Rubin is going to increase this number by about 10 times, where we expect to find at least 200,000 near-Earth objects. And of course, the most practical application or thing to do with all of these near-Earth object discoveries is to try to search them to see if there's anything that might be headed our way, because objects can and do sometimes hit the Earth. Fortunately, most of the time they're small, but for reference, even something the size of a semi-truck, such as this meteor that exploded in the atmosphere above Russia in 2013, can cause quite a lot of damage. This event injured roughly 1,500 people, causing them to seek medical attention, and damaged more than 7,000 buildings in 6 cities across the region. So we, of course, really want to be able to find these things before they hit so that we can hopefully either do something about it or at least warn people that it's coming. Because to date, we've only found 7 asteroids before they have hit the Earth. All of those were found in the past decade, and with only hours at the most to spare before they hit us. That's not a very big number. But fortunately, Rubin is going to help us be able to find more of these objects. And of course, it's the really big ones that we really care about, those things that are big enough to destroy an entire city or wipe out civilization. I always feel like I should say that quietly because it's scary. But fortunately, Rubin is going to Rubin is going to make us very good at finding these so-called city killer asteroids. We expect to find roughly 80% of all of the objects this big or bigger in the entire near-Earth population. And so if we should ever find something that is headed our way, which is unlikely, but if we do, this will hopefully give us enough time, say 10, 20, 30 years or more before a pending impact may occur, to try to be able to do something to avoid that impact, which we've now thankfully had some opportunity to study thanks to NASA's recent DART mission. In addition, I'm sure you've heard a lot about asteroid mining in the media over a number of years now. It's been a pretty hot topic. Asteroids have a lot of very important and helpful minerals in them that would make a big difference to helping some of our shortages here on Earth. And so this is something that with the discoveries that we will find with Rubin, maybe this will make this more feasible someday. One of the populations of objects in the solar system that might be the best to utilize for asteroid mining are objects that can get temporarily captured into orbit around the Earth. We call these mini moons, where they can make a small handful of orbits around the Earth before then returning to orbit around the sun. And we expect to find at least one of these every year with the Rubin Observatory. Also, it's really helpful for us to understand the distribution of volatile materials, so ices and gases, across the solar system. This can help us better understand how the planets and the asteroids formed through a process called accretion. And we can do this by studying comets in the solar system, but also there are a handful of asteroids that have in the past decade or so been discovered to also have activity. As you can see on the left here, this is an asteroid that started to show evidence of a tail as well. The Jupiter Trojan asteroids are another population that Rubin will find a vast increase in the number of. We expect to find roughly 30 times as many Jupiter Trojans as we currently know. The Trojans kind of do a dance with Jupiter, where they're in two groups that always stay in front of or behind Jupiter as they orbit the sun. And studying these objects can tell us more about how these objects got into this type of orbit with Jupiter and how the solar system formed. Also, out in the outer solar system, the trans-Neptunian region, or the Kuiper Belt as we often call it, is a massive belt of asteroids that, based on how they're distributed in the outer solar system, can tell us a lot about the early history of the solar system, when the giant planets changed where they sit in the solar system by a huge amount. And so we can better understand what happened in the early formation of the solar system by looking at these objects. There's about 3,000 of these objects known, and about a dozen or so dwarf planets like Pluto and its large moon Charon, which are shown imaged here by NASA's New Horizons spacecraft that flew past Pluto in 2015. By the way, Pluto is my favorite planet, and we could talk all day about whether or not Pluto should still be called a planet. But I thought I would let you all know that I have been a longtime collaborator with the New Horizons science team, which is a spacecraft that flew past Pluto. And as a longtime collaborator, I have access to some non-public 3D images of Pluto that I would be more than happy, if you're ever looking for another speaker in the future and want to have me back, I would be more than happy to share them with you and tell you more about Pluto. So there's about a dozen or so of these dwarf planets that we have currently found in the outer solar system, like Pluto. And with the Rubin Observatory, we expect to find up to 100 more of these dwarf planets like Pluto. So pretty soon, we could know of about 100 Plutos floating around the outer solar system. And because I, for one, don't really want to have to memorize the names of 100 more planets, maybe that's a reason we shouldn't call Pluto a planet anymore. But I would say that's debatable. In addition, beyond the Kuiper Belt and the trans-Neptunian region is the Oort cloud, which is a spherical shell of comets that sit at the outer edge of the solar system. This comet that DiRAC postdoc Pedro Bernardinelli found is a member of the Oort cloud. And with the Rubin Observatory, we expect to find dozens more of these Oort cloud comets, which again will really increase the number of these things that we found so far and really help us to better understand this Oort cloud at the far outer edges of the solar system. In addition, maybe you've heard that there could be evidence for another large planet that's still lurking undiscovered in the outer solar system. The evidence for this is still unclear, but if it does exist, and if it exists in the part of the sky that Rubin can see, it's likely that we will be able to find this planet with the Rubin Observatory, which would be pretty exciting. And finally, I wanted to just touch on objects that come from beyond the boundaries of our solar system. So like our sun, there are hundreds of billions of stars in our galaxy, and we now know that each of those stars likely hosts at least one planet if not many planets, as well as asteroid belts of their own. And sometimes those asteroids can get thrown out of their planetary systems by the giant planets. And if the trajectories of those asteroids happen to serendipitously intersect our solar system, we get a magnificent opportunity to study the other planetary systems that these objects came from. We have so far found 2 of these so-called interstellar objects, and with the Rubin Observatory, we expect to find anywhere from 1 per year to 1 per month of these objects, and each of those discoveries is going to give us a better understanding of how our solar system fits into the bigger picture. So this is just the tip of the iceberg of all of the many areas within solar system astronomy itself in which we are very excited that we are going to make some amazing discoveries. And this is only one area of astronomy that Rubin is going to enable discoveries in. But I haven't actually told you when all of this is going to happen yet. I think I've said soon many times. The timeline for these big projects are very commonly not on schedule for a number of unforeseen reasons. Even when you plan for contingencies, COVID, of course, didn't help with keeping us on time. But the current schedule, as of a few days ago, is that the LSST camera is expected to be ready to go on sky in December of next year, where we'll get first light with a telescope in January of 2025. And we expect that construction of the Rubin Observatory will be complete in May of 2025, allowing the survey to start sometime in mid to late 2025. So all of this data and all of these exciting discoveries are only 2 years away. And we, as a global astronomy community, have been working very hard in order to be ready for this incredible data set that is coming our way. So as I talked about the DiRAC Institute, we have been working very hard to hire a number of individuals that can really think outside of the box with developing new tools and algorithms that can make amazing discoveries out of these vast data sets. Also, the UW is a partner with the LSST Interdisciplinary Network for Collaboration and Computing, or LINC, which is trying to help bring together astronomers with software engineers and data scientists in order to make even better tools than we as astronomers are typically trained to be able to make, again, to enable more incredible discoveries with the Rubin Observatory. There are also 8 different science collaborations for LSST. These are members of the science community that have self-organized themselves into groups depending on their scientific interests, that have really been working on their own volunteer time to be able to develop tools and algorithms in order to get ready for this flow of data that's going to be coming in just 2 short years. These groups have also done a lot of work to try to help work together with the LSST project in order to help guide how the survey should actually be done in order to make sure that everyone's science is able to get done. As you can imagine, this is a very big effort, and it's really been a global group effort by everyone that's been involved, which I think is a really big accomplishment of the Rubin Observatory so far, even before it started. And finally, I'll mention the Rubin Observatory Community Science Team, which I have now recently joined as a member. We are trying to get the science community ready, again, for the data that's coming by having a mock data set that will look like the Rubin data will look, that will have the tools available on the platform that the real data will be on as well, in order to get everybody used to what the data is going to look like, how they're going to be able to access it, so that as soon as the data is available, they can hit the ground running to start doing this incredible science. And so we are very soon going to be making these incredible discoveries and revolutionizing astronomy on a global scale, but also even locally here within the DiRAC Institute at the University of Washington. So keep an eye out for us. We are going to be, I'm sure, in the news a lot with a lot of our amazing discoveries. And so please keep an eye out for us. I also put on here the links to the Rubin Observatory website and the website for the DiRAC Institute, I very much encourage you to go check out the Rubin Observatory's website if you're interested in learning more. Our education and outreach program group has been putting together some very nice videos to explain what Rubin does and the science that it will be doing. There's even, I think, a couple different games on there. You can practice being a survey astronomer, making discoveries in the images that will come from Rubin, and so those are really fun. And I think there's also an image gallery of the site and the camera and the mirror and all kinds of spectacular images of Rubin as well. So I encourage you to check it out if you're interested. And also, please feel to contact me with any questions that you have about all of this as well. Thank you.
Holy cow, that was exciting. I was just like, I think the overall sense of it is just like it really does feel like astronomy is really going to change, and once that thing starts surveying, I mean, like just the smattering of topics you touched on just lead to so many other questions, and oh my God, I can't believe we're only a couple years away. It's so exciting. Anyways,
Yeah.
I have a bunch of questions, but please, let's ask some questions. This is a really great opportunity. Do we have one in the audience right now?
Oh, yeah, the naming of asteroids and comets is very interesting and has a very long history within solar system science. I think it's still an open question how all of the objects that are discovered by Rubin Observatory are going to be named. The rules for naming objects comes from the International Astronomical Union, and they have very specific picky rules about how things can be named and what they can be named or what they can't be named. But I don't actually know yet. I don't think anybody knows how things are going to be named when they're discovered by these massive observatories.
I had a question from earlier during your talk. But David asked, back to the SpaceX satellites, like how badly will this satellite pollution be as far as observing the data, and do you have technologies in place for blocking that out?
Yeah, I think if I remember right, I think they're going to affect something like 5% of the images that are coming from Rubin. So depending on how you look at it, that's either a big fraction or a small fraction. It's something that a lot of us are pretty worried about. But like the algorithm that I showed that some of our own researchers are developing, we've been trying to figure out ways to be able to remove those streaks from the images in order to make them not a problem anymore. The International Astronomical Union also just started the Dark and Quiet Skies initiative or something like that in order to try to protect the skies and work more with SpaceX and companies like it to figure out how to make these satellites less reflective. And so they've been in conversations with people at SpaceX. I think they've decided to paint them darker so that they're not as reflective, but they've also decided they're going to launch a lot more than they originally said. And so even if they're darker, but there's a lot more of them, I don't know if that actually helps very much. So we're trying, but it's a tricky problem.
Any question here? I have Ula. Could you repeat that question?
Yeah. So the question was about exoplanet science and how well Rubin is going to be detecting these exoplanets and what it might be able to do for exoplanet science. I think in order to be able to directly detect exoplanets, it's a pretty tricky thing to be able to do. And so I don't think that Rubin is actually going to be very good at helping with exoplanet detections because it can't see the planets directly. And usually the way that we detect and discover exoplanets is through indirect methods by looking at the velocity dispersions of these planets, or how they wobble around their stars that might indicate that there's something orbiting the star. And so I think given the cadence with which Rubin is going to be imaging the sky, it's probably not going to give us a whole lot of information about exoplanet science. But there are things like the JWST and other observatories that are much more focused on exoplanet science. And so I think that was one of the things that Rubin decided wasn't a main goal for them to be able to do.
Let's go. What was your name?
I'm Logan.
Logan? Yeah, yeah.
How do you handle like data duplication? If you're going to be running algorithms that are inside data set, you have to package come on. If you're expecting like 3 terabytes per night, you have to like reserve time on the local.
Yeah, so the question is about how we're going to actually handle a huge amount of data that's coming every single night, and how we're going to be able to process that data. If I understood you correctly. Yeah, when we're going to actually do the computations in order to process that data. A lot of that is going to happen during the day when Rubin isn't observing, so it'll observe at the night, during the night, and then the following day, much of that data will be processed. I am not a part of the data management team, but there's a very large data management team for the Rubin Observatory, as you can imagine. And so I believe they're planning to store all of the images that come back, which is an incredible amount of data. But they have their own dedicated, I think there's an entire data center that is going to be dedicated just to the Rubin data that's going to be collected. And it will be processed on a regular basis and made available to the public immediately after it's been obtained. And so the images, all of the sources that are detected for the solar system, all of the solar system objects that can be extracted out of the images, all of that's going to be made available, I think within the next 24 hours or so of the data, the images being obtained. And so that processing is going to be a constant thing that is occurring on a daily basis, which is a lot, to say the least.
I'll go online real quick about the visiting there. Vasuki asked, can we visit the telescope? What other public outreach is planned?
I'm assuming that eventually there will be opportunities for the public to be able to go visit the site. I know right now, actually, our director and associate director of DiRAC are there this week, visiting the site with a group of donors. And so there are some opportunities now to be able to go. And I'm assuming that eventually it will be open to the public to be able to go as well. I don't know if that will be true while the survey is running, or if it will be something that will wait until after the survey is done. I'm not sure.
Eric, why don't you?
A quick question. I was fortunate enough to be in the Atacama Desert a couple of months ago. There are telescopes dotted everywhere. The James Webb is getting huge play. Tonight we've had an opportunity to hear about a telescope I knew very little about. Where is the Rubin in the pantheon of current astronomy? Is this something that we're getting a deep dive on because we're lucky, or is this really the biggest thing going after Webb?
I think to me, and I think much of the astronomy community, this really is the next big thing because of the amount of data that it's going to produce, which is unlike anything that we've had before. It's very different in the type of information it's going to provide compared to some of the other observatories, like some of those in the Atacama Desert, some of these infrared surveys or these radio telescopes or arrays that are getting information. Those help us learn about much different parts of astronomy than what Rubin will be able to do. And so I think Rubin is really poised to change astronomy in a very immense way, but it is not the same as some of the other observatories that are out there. And so it having many of these different observatories, I think, is really important. And so to compare Rubin Observatory to JWST or the Hubble Space Telescope, Rubin, as our director of DiRAC likes to say, is really going to allow us to download the sky. We're going to get all of the information that's available about everything in the visible sky that we are going to be able to download to a database that we can then access and do incredible discoveries with. But observatories like JWST and the Hubble Space Telescope are really good at being able to go very deep at looking at specific parts of the sky. So Rubin is going to make these discoveries, and JWST and HST are going to allow us to go look at those discoveries and get much more detail about those individual objects than we can actually do with the Rubin Observatory. And so they're really an important pairing together that in utilizing both of them will give us a lot more information than just having one or the other.
David Ingram?
Thank you, sir. It's a spectacular project. The problem with information that's coming in on a daily basis makes it quickly obvious to me that we don't have enough astronomers in the entire world to produce all of the data. And you're shaking your head because it's just a well-known fact that you need amateurs and citizen scientists and anybody else out there that can put their hands to the task. So the Seattle Astronomical Society has 500 members. We would like to volunteer them as citizen scientists to data reduction or whatever project. How do we tap in?
Yeah, I agree that I think citizen scientists are incredibly important to astronomy, especially with immense data sets like this. I believe that there are some groups that are preparing for Rubin Observatory that are already trying to gear up for citizen science opportunities with the Rubin Observatory. I think there are also resources that are already becoming available from Rubin's education and outreach program. And so if you go look at the Rubin Observatory website, I think there is information on there about citizen science opportunities that are being put together by the Rubin Observatory project itself. But I know that there are a number of other groups within the astronomy community itself that also, in order to help fuel their own science that they want to do, have put together community scientist or citizen scientist projects that the public can then go and be able to be a part of as well. And so I'm sure there are going to be a number of those that are going to start popping up as well once the Rubin data starts to come in.
I have a question from Vasuki. I think you touched on this a little bit, but what is the wavelength range for observation in any specific, any spectroscopic observations planned?
Trying to remember the wavelength. It's an optical telescope, so it's really limited to the visible range. It kind of pushes into the infrared range and the UV range a little bit, but it's really trying to span as much of the visible range as we can, and I don't remember the numbers off the top of my head. As far as spectra go, Rubin isn't going to offer any kind of spectra for these objects. But again, it'll make these discoveries that then people can go use other observatories in order to take spectra of objects that they're particularly interested in.
Was there another question over here? Eric and Dan? Yeah, Dan. Yeah.
So I've been a professor of medicine for about 30 years, and there are LLMs now that know more than I do, and they've been developed within the last 6 weeks. The rate of acceleration for LLMs is astonishing. I admire citizen science deeply. I admire professional astronomers deeply. What is DiRAC doing about using machine learning and pattern recognition and other sorts of things to accelerate that pattern, that data analysis?
Yeah, machine learning and artificial intelligence, I think, are going to be really important for how big this data set is going to be. And some of the people within the DiRAC Institute have already started looking at options for using machine learning for this. I think I haven't done this myself, so I don't understand all of the limitations for using machine learning for astronomy. I think my understanding, there are some tough things about being able to use machine learning for doing astronomical discovery. But I know that there are people both within DiRAC and the astronomy community that are trying to push those boundaries and see what we can do, because having something like that as a tool that we can use when we have this incredible amount of data, I think would be really, really helpful. So people are definitely thinking about it. But I don't know that that has advanced very far yet, but maybe we need the data set to be able to start doing something with it. Yeah.
Dan?
Yeah, we will absolutely have some issues with weather. The mountaintop in Chile where the Rubin Observatory is being constructed is one of the best sites in the world, being so high up in the atmosphere. So the amount of weather and interference from things like the weather should hopefully be minimized. It will end up producing some gaps in our data, but Rubin is going to image the entire sky that's visible to it every 3 nights. And then it's going to do that again for 10 years. And so even if there are nights where it can't observe certain parts of the sky, it's going to cover that part of the sky many times over its lifetime. And so I think those gaps shouldn't largely be really important. It depends on what your science is that you're trying to do. If you miss a specific night, that might be the one night that you could have seen, or a number of nights you could have seen that interstellar object that was coming through the solar system really close to us or something. And so there will be some things that will be what's the word I'm looking for, that will be affected by that in a very negative way. But I think overall, it shouldn't be too much of a problem.
No, just 2 more questions. I wanted to ask, so I know in astronomy a big problem, if you will, has been, just waiting time and access to use telescopes, and everybody has all these ideas and things. But so does this telescope effectively just shift that whole landscape of like, if the data is accessible to everyone, will there be giant waits to use the telescope and specific things? It's just doing its things. Everybody has free access, so there's no waits.
Yeah. Rubin Observatory is set up to just be doing its own thing. It's going to be surveying the sky for the 10 years that it's in operation, and so it won't be available for people to be able to do their own specific requests of what it's looking at. But one of the catchphrases for the Rubin Observatory is that it's going to democratize astronomy, because it's getting this incredible amount of information that's going to immediately be available. There are data rights holders that will be able to have access to the data before other people will be able to. And so the US is one of those data rights holders. So anybody in the US would be able to have access to the data immediately. And then after some proprietary period, it becomes publicly available to anybody as well. And so for those people that haven't bought in to be data rights holders, there will be a bit more of a wait. But the point is that this incredible data set is going to be immediately available to everybody. And so it's really making it accessible to everybody and helping make sure that people who don't traditionally have access to telescope time or to do this kind of science, that they will be able to do the same level of science if they can gain the expertise to know how to access the data as anybody who normally has that kind of access.
So what you're saying is I could discover a supernova, potentially.
Yeah.
Yeah, that'd be awesome. Please, maybe you can teach me on the side on how to do this. Just follow up on that, but before the last question, so does the field of astronomy need more astronomers and astrophysicists and people in the field coming up, like the people in high school and middle school and undergrad? Like, it's a good time to be in this field, right? Like, where do we need more people?
Yeah, I think it's a fantastic time for people to be coming into astronomy as we're getting ready for this observatory to start soon. And so I think we can, I mean, with this amount of data, we can always use more people in order to be able to do all of the astronomy that's going to be possible with this type of data set. I think the limiting factor, though, is what kind of availability there is for graduate students to be able to be funded and to be housed in departments. And then once you graduate, to be able to find a job in astronomy as well beyond that. And so there's a pretty big cap on the availability of jobs within the field, or even spots within graduate school programs based on what universities are able to support. And so we can always use more people, but we also need more money and more funding to be able to have more people come through these programs and be able to come into the field. So that's really what we need is money, which is what it always comes down to.
Well, exciting times. Last question. We're gonna throw it back a little bit because everybody got really excited when you mentioned Pluto, and so so David asked a lot of great questions. He was asking about question. Oh, he said something about do you know why I don't know about this, but do you know why the Pluto atmosphere collapsed recently? I didn't hear about this, but is there something about the Pluto atmosphere that any fun facts about that?
I don't know a whole lot about the atmosphere of Pluto, but I know it is one of the biggest topics that's being talked about with Pluto because of the New Horizons mission. And so I think one of the things about the Pluto atmosphere is that as Pluto gets closer and farther away from the sun, because it's on this very elongated orbit, it's thought that the atmosphere can actually part of it can freeze out onto the surface of Pluto, and then it kind of re-aerates and goes back into the atmosphere. And there's kind of this periodic effect as Pluto is orbiting the sun. And so I think that might be what is being referred to. But I don't know much more than that.
Do you have a favorite fact about Pluto?
I do, and I could tell you now, or I could tell you if you want me to come back.
Yeah, I know. Give us the teaser now.
I think the most amazing discovery that was made at Pluto is that it has a boiling lake of toothpaste ice on a big part of its surface.
So
which sounds crazy.
Very soon. We'll have you back very soon to discuss that then. While I have the Zoom people here, just wanted to thank Sarah. Thank you so much for this amazing presentation. One more time, give it up on Zoom. Some applause there. This is very inspiring, but also very informative. Like, I've seen a bunch of these presentations as well too. They're all great, a lot of information, but I love your balance of, it's very welcoming to all kinds of levels. So I really, really appreciate you driving down here, making time just for a little old us and our Zoom community. But I promise you, the seeds are planted, and we'll spread the love on this. This is very, very excited, and just thankful that we can be a part of it and for your time. So, all right, I'm gonna say good night to Zoom, and just one more time for Professor Sarah. Awesome.
Thank you so much
Okay.
for having me.
All right. See you, Zoom world. Peace out. I'm just gonna do that. Let's see.